In this video, I'm going to discuss equipotentials and sort of how a uniform electric field arises. Okay, so if I were to draw a dipole, right? So we've got a positive charge and we've got a negative charge, right? And I'm to draw the the electric field that arises because of this. Okay, and then, remember that these are going to kind of combine like this, and then we have, our lines over here. Okay, so essentially what happens is that at certain positions, there is a point where the potential difference is actually zero. So an equipotential is where I could move where the potential difference would be zero. So an equipotential line, I guess, is a line where potential difference is zero. Okay? It requires no work to move along this line. Okay? Now, equipotential lines, okay, if we're looking at any sort of electric field, sorry, I keep saying magnetic field, are perpendicular to the electric field lines. Okay? So if I were to draw one, okay, here, it would kind of be like in that direction, or have one kind of like right here, okay, or one right perfectly in the middle. It'll go like this, or okay. So in order to move along this line, right, along this path, it takes zero work. There is no potential difference. Okay. Now there's another common example. So remember, this is a non-uniform field, so non-uniform. Okay, but we also have a case where we do have a uniform field. So let me draw an example of that. Okay. Okay, so this is a parallel plate. So if we have two like metal plates, okay, across from one another, what happens is let's say one of the plates is positively charged, and we'll talk about how all this can actually happen. And a negatively charged plate, you're going to have a uniform electric field that occurs in between them. So this is an example of a uniform field, okay, like an example like we saw before, okay? And so parallel, perpendicular to these lines are like our equipotential lines, right? So up and down we have these equipotential lines, okay? Now let's say that maybe there's a 20 volt potential difference. So that means it would be like 20 volts over here and 0 volts over here. So in increments you'd have like 15, 10, 5, in equal distant increments. So this would be like 15, this would be 10, this would be 5 volts, okay, all along that line. Okay, now another instance where we have equipotentials is on the surface of a conducting sphere. So a conducting sphere, okay, remember we said on the surface we have a big conducting sphere. All those electrons are going to move out and they're going to spread themselves out so they're evenly distributed across the surface of the conducting sphere. Okay, so we say that the entire surface is considered an equipotential surface because all of the charge is evenly distributed. So that's equipotentials, and we'll go a little bit in the next video into detail about performing some calculations in terms of work and in terms of electric field with these ideas.